Welcome to this ATA Insights webinar. Thank you for your ongoing interest and support of our webinar program. Today's session will begin in 2 minutes. ATA Insights Webinars is an online platform for the dissemination of professional renewable energy knowledge across international borders. Our aim is to democratize access to information, for innovation to spread faster, and to make the industry more competitive. And we do this through our online sessions, open to all our members. Every year, we do more than 100 sessions with over 250 speakers, 50,000 attendees from more than 50 countries. To participate in the session today, use the chat on the right-hand side to introduce yourself, your company, and where you're joining from. Under the screen, you will find the Q&A box, where you can send your questions for the speakers. We will get to as many as we can today. We're recording this session, and we will send you a link to the materials in a few days. Please consider supporting our content creation for the webinar program. Contact us on the email on screen. Welcome everyone to this online webinar about optimizing your PV project by switching standard 670 watt PERC cell modules. With me today, I've got two experts in this topic, and I hope that you're going to learn immensely in order to inform your decisions going forward about the modules that you pick for your PV projects. And I'd like to ask them to introduce themselves so that you can get to know them a little bit better. So Nasir, please, if you could introduce yourself.
Yeah, thank you very much, Belin. My name is Nasir Khan, and I'm the sales manager for Trina Solar. I'm based here in Dubai, and I'm basically looking after Middle East and Africa market. Thank you.
Thank you very much, Nasir. And now I'd like to ask Omar to please introduce yourself.
Sure. Hi, everybody. My name is Omar Al-Darwish. I'm the lead applications engineer for SMA Middle East and Africa.
Excellent. Thank you very much, both of you. And I can see from the people in the audience that there are people here from Italy, from Istanbul. We have someone from Libya, also from Kenya, Johannesburg. So it's very diverse. Who else is in the audience? Please introduce yourselves. We love to see it. But just as a matter of to explain to you exactly how this works, in case this is your first time, although I suspect probably isn't, we're going to use the chat for to introduce yourselves, to chat, and 11 and 2, welcome. And we also have the Q&A box, which is at the bottom of your screen, where it says Q&A, or might say something different, depending on what language you're using for your program. So in there, you can actually send us questions, and they're easy for us to manage, because it gives us a lot of other options. So please use that for your questions, because we do have time at the end of the session to take them. And both Nasir and Omar just love answering those questions that you sent. So the system today, the structure is very, very simple. We're going to have two specific presentations from Nasir and Omar, and then after that we will take the questions. You can send your questions at any time, okay? We will just catch them afterwards, and we are recording this session, so you will have access to both the recordings and also the materials. So don't worry about that. You will be able to see them again. You will be able to share them with your colleagues, okay? So without further ado, I'd like Nasir, please, if you can prepare your presentation and get ready for that. And whilst you're preparing, I'd just like to say hi to other people who are here in the. It feels like today we're in a very cozy group. Thank you very much, guys, for being so active in the chat. So we have people from Switzerland, from Gaza, from Egypt. From Nigeria. There's a little bit of everything. Welcome, everyone. I hope that more people from many other countries also get to join us. If you can put that into a larger screen, please, Nasir, because we can see it already, but it's just, okay, perfect. So this is ready for you now. Just take yeah, there we go. Okay, off you go then. Thank you very much.
Yeah, thank you very much, Belin, and welcome everyone to this webinar. So we have seen that in last 1 year, due to several factors affecting the supply chain of PV modules, the cost of PV modules has significantly shot up. And as PV modules are the major components of solar plant, of any solar plant, so all our major customers and clients have started the exercise of optimizing the PV plants. So in my presentation today, I would be highlighting the major areas where our ultra high power Vertex 670 module, brings saving to our customers, and then it results in a very optimized PV plants. So, but before that,
are you okay, Nasir?
yeah, actually, I was not able to change the slide for some reason.
Oh, okay, no, but it works now. We can see it. So maybe it takes a few seconds. Just take that into consideration.
Yes. So just a brief introduction about our company. So I'm proud to be part of one of the oldest PV module manufacturer in the industry, Trina Solar. We were established in 1997, making us one of the oldest PV module manufacturer in the industry. We have our headquarters in Chengdu, China, and we have footprint in more than 100 countries worldwide. And until now, we have a total shipments of 70 gigawatt. That is, we have delivered more than 70 gigawatt of PV modules. And we have more than 15,000 employees in our company. So now moving forward, and this 70 gigawatt, as I said, that this has been achieved with the help of our 6 factories. We have 4 factories in China and 2 factories overseas, one in Vietnam and another one in Thailand. So the combined capacity of all our factories is more than 50 gigawatt, and we have our own, cell capacity of more than 35 gigawatt. Now this is our Vertex family of modules, as you can see. So when we say our Vertex series of modules, we mean that in these particular modules, we are using a cell size of 210 mm cells, and these cells are, for this 550, 600 and our recently launched 670 watt modules. These are around these are 210 mm half cut cells, and for other our modules, these are like 210 mm third cut set. So we in total we have our Vertex modules ranging from starting from 405 watt to 670 watt. So when our customer they choose our Vertex modules, so basically what they are getting is they are getting a PV module that has 30 to 90 watt more capacity than other modules available in the market. Now let me give you a brief introduction of our latest Vertex 670. This is our latest addition in our Vertex family that we have launched. It is an ultra high power module having a highest power of 670 watt that is currently available in the market. It has a high capacity. It has a high efficiency of 21.6%. And there is another feature I would like to highlight, that is the low VOC feature. It has a low VOC of 41.7 watt. And with the help of this low VOC, and by the way, this low VOC, it is inherent quality in all our Vertex modules. So with this low VOC, we are able to connect more number of modules in the series to form a string. So we have a longer and more powerful strings. So please keep this in mind that we have more powerful and longer strings. So with the help of, and the major BOS saving that we are able to realize in PV projects come because of these longer strings. And so moving on further, let me just tell you that when our customer opt for our Vertex 670 watt modules, with the help of high powerful string, basically they are having a lot of saving in the electrical cost, in basically electrical system cost, sorry, in civil structure cost, in logistics. So now moving over to the logistics cost, because of high power bin of 670 watt, basically we can pack more number of modules in a container. So when our customers are going for 670 watt modules with Vertex 670 watt modules, per container, they are having the maximum power per container. They are having more than like 12% power per container. So that what this means for their project is that they will have lesser number of containers for their projects. So to reach that power, they will require lesser number of containers. So we have found out that since we are giving additional power of like 39 kilowatt per container, so there is a saving of 0.4 to 0.5 cents. 0.4 to 0.5 cents US cents per watt saving with logistic cost alone. So, and this is just in form of logistics. Then now moving over further, we can see that there would be saving in electrical systems cost, in mounting structure cost and civil cost. And all this saving is basically realized with significant reduction in the number of strings. So when I say that significant reduction in the number of strings, what we mean is that, for example, if you have a project of a size of 1.6 megawatt, so for a 182 mm cell module, you will require 100 number of, 100 number of strings to reach that capacity. Whereas if you are using Vertex 670 watt modules, you will only have 75 number of strings. So you will have 25% reduction in the total number of strings for your project. So what we can say is that for every 4 strings of 182 mm cell modules, you will only have 3 strings of Vertex. So in that case, so in that sense, you are saving a lot in the total number of strings when we extrapolate it to your project. Now coming to the electrical system cost, as I just said, for example, taking a case of string inverter. So if we are taking a case of 200 kilowatt string inverter, basically to power on a 200 kilowatt string inverter, you only require 12 number of strings of Vertex 670 compared to 16 number of strings. It would be in a ratio of 3:4. So you are saving 4 strings of 182 mm cell when our customers are going for Vertex 670. And usually the common practice of connecting a 182 mm cell module is that they are connected using a Y connector to reach the current level of each input of MPPT. So in our modules, what our strings, what string of Vertex 670 are connected, they are connected directly to each input of MPPT. In that case, our strings are more balanced without any extra component like Y connectors. And yes, there would be lesser number of cable since 2 strings are connected, and then there's one cable that goes directly to each input. So you have much more balanced system with lesser number of cables. And now going to the same thing before moving forward to this mounting structures. Let me tell you, the same philosophy is applicable on central inverters as well. So for central inverters, then you will have since each string is connected to a string combiner box, so you will have smaller string combiner boxes. Now moving over to mounting structures. So there are 2 types of orientations in which the modules are mounted on a mounting structure. So first of all, let us take a case of a fixed tilt system. So for a fixed tilt system, there are 2 types of orientation, portrait as well as landscape. So if we take, for example, if we take portrait, then there would be a saving of 5%. And please bear in mind that we are using the same 200 kilowatt inverter as an example in this case. So you will have 12 number of strings, but the total number of modules will be less. So the total number of modules will be less. So it will take lesser area. So you will have 5% reduction if you are mounting your modules on a portrait orientation. And when we move over to landscape orientation, then there is a significant advantage of 13%. So as you can see in this diagram, in this slide, that when 12 strings are connected on a landscape orientation, there is a significant reduction of 13%. So in that case, as you know, that there will be lesser number of mounting structure required, and by lesser mounting structure, we means that our customer are saving on the steel, on purlins, and then the same thing is translated on even on the civil costs, as there will be smaller trenches. The trenches will be smaller, and in other such areas. Now moving over to trackers. Now for the case of trackers. For the trackers, what we advise our customers in if they want to go for optimization is to select the length of the tracker such that they can mount three numbers of Vertex, three number of Vertex 670 to select their trackers in the multiple of three strings of Vertex. So they can either go for like 1P configuration. So in case of 1P configuration, 1P one row configuration, the length of the tracker should be such that they can mount like three strings of Vertex. And then if they are going for 1P bi-row tracker, it should be such that they can mount 1.5 strings of Vertex, 1.5 string of Vertex. In that case, they can have like three strings of Vertex, per tracker, compared to 4 strings of 182 modules. So in this diagram, you can see that in blue, it shows the configuration of Vertex on a tracker, and in red, you can see configuration of 182 cell on trackers. So as you can see from this figure, that you only require four rows of Vertex 670 compared to around 5.5 rows of 182 cell. So in that case, our customers are directly saving like 1.5 rows of trackers. So they have, as I said, since they would be saving on the tracker, on each tracker, on each row of tracker, and also in other associated civil cost involved. And as you can see from this figure, this red dot, either it can be a string inverter or it can be a central inverter. So the lines coming to these red dots are the cables joining. And so if you compare it with the right hand side diagram, so there as you can see, there is evidently lesser number of cables, lesser number of DC cables involved. So the customer is also saving on they can optimize their plant design by saving a lot of electrical system cost. Now, recently we have, not us, but Fraunhofer Institute of Europe, they have done a value assessment study. So in just a little bit of introduction about Fraunhofer Institute. Fraunhofer Institute is the largest solar institute in Europe, and they have done a study in 2 locations, Germany and Spain. In Germany, they had a system, they had a 10 megawatt system using monofacial module on fixed tilt. In Spain, they had 100 megawatt system on using bifacial module on 1P trackers. And in this study, they use 6 different type of PV modules, starting from 455 to 665 watt peak power wins, and 455 and all these were using different cell sizes. For example, 455 was using 166 cell, and 550 were using 182. And in the industry, for example, 166 is denoted by M6, 182 by M10. And rest other modules, 550, 600, and 665 were using 210 modules that was represented by Trina Solus module. So in this study, what they have found out that in both the system, irrespective of the mounting structure, so there were significant savings. So in Germany, in the 10 megawatt fixed tilt system, there was a significant saving in capex, and there was, if you compare it from 540 to 665, there was a saving of 2 euro cents. 2 euro cent, which can be directly converted, which was directly reflected in the LCOE cost, and the LCOE cost went down by 4.1%. In the same way, in the system used in Spain, there was a saving of like 1 euro cents, with the LCOE cost went down by 1.9%. So as you can see, in both these systems, there was significant savings when the customer used our Vertex 670 watt module, because again, I would like to say that to reach since you have lesser number of strings, so to reach the capacity of your plant, you require lesser number of modules. And as lesser number of modules so are required for to reach the capacity of the plant, so all the associated equipments or all the civil cost, all the work associated are also significantly reduced. So now this is one project that we have commissioned in China. So in this project, the size of the project was 120 megawatt. So it was commissioned using our 670 Vertex bifacial module. And this project was commissioned in, I think, around mid of September this year, 2021. So in China. So we have also successfully commissioned one project, and we have one project under our belt. We have all the certifications ready, and we have been working with our partners like SMA. And as Omar is going to explain later in the slides, that we are fully compatible with all inverters, all trackers currently available in the market. We are not even compatible, but we have also worked out on like the most optimized solution for our customers to reduce the cost. So yeah, that's it. That's my presentation. So over to you, Belin. Thank you very much.
Thank you very much, Nasir. If I can ask you to stop sharing your screen. Thank you very much. And the good news, guys, is that we have people that are answering questions also in the background. So if you send your questions, you might find that actually they get answers very, very quickly. So that's great news. And Omar, now it's on to you. If you can please give us, put up your presentation. That'll be highly appreciated. And keep them coming, guys. I've been really proud. You guys have been sending a lot of questions. Well done. Keep them coming. Omar, yeah, we can see your screen.
Perfect.
We can hear you, so go right ahead.
All right, amazing. Thank you, Nasir. Thank you, Belin, again. I'll be sort of carrying over the story from the module side towards the inverter side today for the next like 10, 15 minutes. Of course, we start with greetings from our legal department. Has to be flashed for a couple of seconds here, and then we kick off, right? So this is going to be my only marketing slide. I promise you that. I'm pretty sure you guys are well acquainted with SMA. We've been 40 plus years in the business. We're 3,000 employees strong, over 100 gigawatts of shipped inverter capacity across 190 countries. And our R&D is strong with 1,200 patents and counting. Our key financials are also available on our website, so I won't dwell on these. We're a publicly traded company. You're welcome to check our balance sheets on the website. Right, so the plan is today I'm going to sort of tackle this from a technical perspective for the technical audience out here. So I'll just slowly go over, or very quickly go over the fundamentals, why ultra-high power modules are what they are, and how that affects sort of the inverter interface. And then I will chat a little bit about our sort of approach to optimizing utility-scale power plants, especially with ultra-high power modules. Right? So you've probably seen this before. This just shows you the development of semiconductor NPV ingots, right? So the 12 or the M12 has been really popular in the semiconductor industry, actually starting 2005, but we now see it creeping into the PV modules, right? With mainly Trina championing this innovation. And you're more or less, that has implications on one thing only, which is the short circuit current, right? So if you think of a PV cell, what is a PV cell? A PV cell is a irradiance controlled current source, right? Where your irradiance is directly proportional to area, and hence if you have a larger cell area, you're going to have larger currents. Right? The voltage of your cell is more or less a function of temperature, and I will be sort of talking about why that is important in a couple of slides. Right? So key takeaway here: bigger cells, more current. Right? And bifaciality, well, basically by going bifacial, you give more room. Maybe I should switch to a pointer here. Just give me a second. All right, so yeah, by switching to a bifacial module, you're giving more room for light to cross into the cell, which basically means you're just going to increase current. Right? So higher irradiance plus higher area equals higher current. So that sort of results in these numbers, which people are sort of worried about, right? So you've been probably most of your life dealing with 10 amps or maybe more recently 12 amps. of short circuit current, 13 amps, but all of a sudden now you start to see modules with 18, 19 amps of short circuit current. And that has sort of some implications on the inverter module interface, right? And to be very specific, there are two values which you should be looking at. You should be looking at your IMP and the ISC on the module side, and their counterparts on the inverters are the operating current of the inverter and the short circuit capability of the inverter, right? And these are not to be confused with each other. One is an absolute limit. So your short circuit is actually your upper band, and then the operating current you could be optimizing around, right? The short circuit current is mainly a safety requirement, right? So imagine the inverter is not going to short itself, it's not going to draw short circuit current from the modules. But in case there's a short circuit happening somewhere or fault happening somewhere, we have to make sure that the inverter is able to interrupt the short circuit current that is coming from the modules, right? So when you're starting to sort of interface a module with an inverter, you should be first looking at short circuit current. I should be able to match or let's say exceed the short circuit capability or the short circuit current level of my modules at inverter level, right? The story is different with operating current. Operating current can be optimized around, and I get this question a lot, right? So you get people asking, but the operating current of my module is higher than the operating current of my inverter, so these are not compatible. But if you really look at the data and you simulate your plant, you barely operate at operating current, right? So if you see, these are field data from Jordan, right? From a tracking and a fixed system. And most of the time, I would say, I'm comfortably saying 95% of the time, you're actually operating below STC current, right? That is because you've basically got light-induced degradation, you've got soiling, you've got air mass, your azimuth and tilt are not perfect, right? And you've also got probably some shadowing going on. So you're really very rarely operating at STC or above STC. And for that reason, you basically can operate, let's say, a higher IMP than your inverter. And that is completely fine, because first of all, most of the time you're operating below. And then if you're operating above, you're basically just clipping, right? Now off to sort of the inverter capability or compatibility side, right? So most of, let's say, the problems or troubles that come from high short circuit current modules are due to multi-amputee inverters, right? So you can imagine a multi-amputee inverter has to comply to the short circuit current requirement at MPP level, right? Versus a single MPP inverter really only needs to do it at one spot, right? And for us, we call this a sort of a sums versus unions problem, right? 4 MPPTs with 40 amps is not really equivalent to 1 MPP with 160 amps. And that can be illustrated really if you have, let's say, a short circuit current of 30 amps. That means you can only connect 30 amps here, 30 amps here, 30 amps here, and 30 amps here, right? But 10 amps are actually lost on each MPP, right? Whereas if you have them lumped in 1 MPP, then you're able to actually connect an additional string here, right? So this extra bottleneck can sometimes cause some problems. And that is why we recommend going for a single MPPT inverter in general, specifically with higher, ultra-high power modules. For further optimization, I would sort of like to go through 4 caveats of multi versus single MPPT inverters in utility scale power plants. Right, so you've already optimized your number of strings by switching to Trina 670, right, which has really good implications on your BOS. And now we start to discuss your plant's architecture and how that also further optimizes your plants. First is sort of the MPPT myth, right? So actually, if you really think about maximum power point tracking should be called maximum power voltage tracking. So you're not tracking the power, you're actually tracking the voltage. Your array starts at open circuit, and then your inverter will reduce the impedance as seen by the modules towards a lower value so that we can extract more power, right? So what you're really changing here is the voltage, not changing anything else, right? And if you now look at the cell side, voltage is mainly a function of temperature, right? So these are standard IV curves, you can find them on any module. And you see if you actually change the irradiance by at least 80%, right? Going from 1000 down to 200, your voltage doesn't change much. Right? Your voltage is mostly constant. Whereas if you change the temperature, that's where you have sort of a delta in voltage, right? And we just say basically your plant is operating more or less at the same voltage, whether it was in the morning or at noon, right? And that is sort of, this is real world data from actually a really much harsher environment like a rooftop, where you can have shading, you can have probably differential temperature effects between your strings, and you're still, as soon as the power plant wakes up, your voltage is ramped up and it actually stays around the same voltage, right? And whether you are at 55 kilowatts or you're at 500 kilowatt, the voltage really doesn't deviate that much. And in that case, you really don't need MPPTs to extract more power, right? If all of my voltage is the same, even on east-west configurations, I actually recommend going for a single MPPT, because your voltage is a function of temperature, it's not a function of irradiance. So any mismatch factors are actually not affecting voltage, they're mainly affecting current, right? That's sort of what I call the MPPT myth, right? More MPPTs do not necessarily equal more yield. And if they do, it's really marginal. Going from 0 MPPTs to 1 MPPT is not the same as going from 1 MPPT to 100. And that is sort of, yeah, at least the MPPT myth. Right? Now we sort of switch over to more, let's say, recent development, which is higher and higher DCAC ratios. Basically, let's say over the past 5 years, we've seen people actually going from 110 to 120, even to 150 and 180 DC to AC ratio, right? And if you're sort of, if you think about a high DC AC ratio plant, you're really clipping most of the time, right? So if you're clipping, that means you're by definition off MPP and you're not using the MPPT at all, right? And I don't think anybody wants to be in the business of buying stuff you don't use, right? So what I tell my clients is, generate these curves and calculate the percentage of energy that you're generating off MPP, right? And that's going to be a majority of your energy actually is being generated off MPP because you're clipping. And yeah, this is actually a plant in the US with up to, I think, 180 or 200% overloading. And we see more and more of our clients are actually wanting to pack more DC against more DC power behind their AC capacities. All right, and now we come to the architecture part, right? So if you think of a PV power plant, you come and you want to design a power plant, your connection point is more or less pinned down by site, and your PV modules are pinned down by site, right? So you can't really change much around. And now you want to connect the two and you have an inverter, right? You have the DC side of the inverter, most probably in utility scale, operating in 1500 volt DC, and then definitely below 800 volt AC on the AC side. And if you think of an inverter with a multi-MPPT configuration, basically your combiner box is sort of conjoined. I call them conjoined twins, right? At birth, they're conjoined with the inverter. And this gives you really only one single degree of freedom. And if you want to optimize, what you do is you basically do your calculations and everything tries to push the inverter towards the connection point, right? Your cabling costs are lower, you're clipping less, your AC losses are less, your communication infrastructure is cheaper, and inverter operation maintenance is actually more convenient than the lots, right? But you can't really do that with multi-Amputee inverters because what you're using here are 6 or maybe 10 mm square cables, and this can get, first of all, what we call the macaroni effect, right? So you don't want to have hundreds of these cables going through your plants for hundreds of meters. That's a nightmare O&M-wise. Second of all, they're extremely expensive. If you think about a 6 or a 10 mm cable, you're actually really buying insulation. You're not buying copper, right? So as the DC cable grows in cross-section, the amount of current actually grows quadratically, and the amount of insulation grows linearly. Right? So you're able to sort of reduce your insulation costs drastically, right? So 10 mm square cables are more expensive than 100 square mm cable, right? So with this inverter, you're sort of, or with this architecture, back to square one, or even worse, you're stuck with inverters close to the modules, and you have really long AC cable home runs. Right? So you're being penalized for your clipping losses very early on, and then you're actually carrying all your AC losses 24/7. Right? And then, of course, has implications on running comm cables through the plant. Your trenches become more complicated, and yeah, basically it has a lot of caveats, right? So what is the natural thing to do? Well, you split them, right? And this gives you 2 degrees of freedom. You can optimize the location of your PV inverter as well as your combiner box. So that gives, let's say, more space for optimization. And they're linked sort of with up to 300 square mm, really long home runs with thicker cables. This just gives you, let's say, optimal capacity, or let's say optimal operational capacity at plant level. The final caveat is what I love to call paralysis by analysis, right? And that is mainly string monitoring. With string monitoring, you get a lot of data, but we don't think you get a lot of information out of the data. So there are distinctions between what is data and what is information, right? And it truly is the case that you really have to be thinking about this backwards, right? You want to say, what are the parameters I want to infer of the plant? What are the operating parameters? And what is the minimum amount of data that I can collect to reliably infer this parameter, right? It doesn't go the other way around. What data do I have? And let's collect all the data, right? So you only measure maybe 1 or 2 back module temperature. You don't measure the back module temperature across all of your strings, right? So the same goes for string monitoring. All the failures will be detected. Even if a string is underperforming, that will be detected directly by ratios, right? And basically going resolution from zone to string doesn't really extract much more information. It just gives you more data, right? And at the end of the day, we just need information. We don't need data. Right? And yeah, finally, I just want to say basically, we've sort of come a long way in the PV industry, and we sometimes deviate from what is truly PV engineering. PV plant engineering is reliability or longevity engineering, right? And the first rule is having less failures is just having less things, right? So if I look at an inverter and I see everything, sort of a lot of things going on inside an inverter, that sort of scares me, right? And it truly is that you can do more by having more, but if you can do the same with less, that is, in our opinion, what is true engineering, right? Because then you're reducing your failures by definition. And yeah, thank you so much for tuning in. Back to you, Glenn.
Thank you very much, Omar, and thank you very much, Nasir, for both your presentations. If you can remove that off the screen, let me see, I can help you. Oh, there we go. Yeah, thank you. Okay, let's go with some questions. I'm going to start with one question from the audience for Omar. I'm going to start there, and then I have some questions prepared as well. Don't forget, guys, you can keep sending questions, not only because we have some time now, but also because we've got people from Trina and from the companies actually answering them. So if you send them, they can also get, if we have too many, you know, we also have people there like answering them. So Omar, the first question that someone just sent through like a minute ago says, do you think it's more important for a string inverter to have intelligent MPPT algorithm like Optitrack, or to have more MPPT for reducing electrical mismatch due to partial shading of one or more strings?
All right. So thank you for referencing Optitrack, which is now, this is a SMA patented technology, right? And of course, I would be going with a more intelligent MPPT tracker than more MPPTs, right? Because then you have less hardware and you're able to extract more or less the same, right? So for us, for those of you who don't know, Optitrack is basically our global MPP tracking algorithm, which is very intelligent, patented, and is basically has been shown also by Fraunhofer to extract more or less the same yield, even under partial shading conditions.
Excellent. Thank you very much, Omar. So now I'll move, Nasir, I have 2 questions here for you, if I may. So the first is, how do large size modules realize such high efficiency in output? Could you explain the key factors that make them able to achieve this?
Yes, sure. Actually, we are using basically 4 technologies to achieve such high efficiency. So these are the use of 210 mm cell. We are using another technology called non-destructive cutting, then multiple busbar and high density interconnection. So let me go through all these technologies one by one. So as you know, in our Vertex series, we are using 210 mm cell. So this is the largest cell size that can be cut out from a G12 wafer. So we are using that cell, and this is the largest, and I can say that most advanced cell size currently available in the market. So this technology, I mean, it significantly increases the efficiency of our modules. Then the second thing is, for example, if we take this 670 watt module, 670 watt Vertex. So here we are using 210 mm half cut cell. So each cell, 210 mm cell, it is half cut. So usually the conventional method of cutting is that these cells are cut using at a very high temperature. They are laser cut at high temperature, and then a mechanical force is applied on them. So with this mechanical force, actually the edges of the cut cells they are very rough, and it reduces the reliability of the half cut cell. It almost makes the mechanical performance of the cells half cut cell like half of the full cell. So, but we are using a technology that is called non-destructive cutting. So here we are cutting the cell at a very low temperature, and then we are not using mechanical force on the cells. So basically the cells are cut at low temperature, and then they are not cut but separated using this expansion and contraction technique. So then it results in very smoother edges of the cell, and the mechanical performance when tested for these cells are of half cut cell are almost similar to a full cut cell. Then thirdly, we are using high density interconnection. So high density interconnection means usually the common practice, the conventional method is usually they keep very high gap, or otherwise there is another method that is used to connect the cells, that is called shingling or overlapping. So with this overlapping of the cell, then what happens is one cell is on top of the other cell, which then further puts pressure on the cell at the bottom, and it might result in micro crack. So we are using high density interconnection, and lastly we are using basically this multiple bus bar. So basically what we are doing is usually we are using like 12 bus bars in a cell, and for these bus bar what we are doing is we are using round ribbons. So with the round ribbons, actually there is very low shading, and then by using multiple bus bar we significantly reduce the current path. So there also, I mean, and this is another way of increasing the efficiency of the cell. So I hope it answers your question, all these 4 techniques.
Yes, thank you very much. Thank you very much, Nasir. So one more question following up on the last one. The Vertex series has a very high number of, the Vertex series has high current and lower voltage parameters. Could you tell us about the product's compatibility with the inverters, with the mainstream inverters that we all know?
Yeah, sure. Actually, as you know, I mean, we maintain a very low VOCs. We maintain a very low VOC so that more number of modules can be connected in a string. But on the other hand, as you know, these modules have higher current. But what we know is that the current inverter manufacturer, I mean, we are fully compatible with them. And the second thing is what I can say on this low current is that since there are a lot of BOS saving in electrical system, for example, the basic concern apart from being compatible with the inverter is the ohmic losses in the system for our customers. So but with that current also, we give our customers a flexibility of either going for 4 mm square cable or like a 6 mm square cable. And as you know, ohmic losses are dependent on the resistance, and the resistance is directly proportional to the length. So, but the length of the cable are required. I mean, there is lesser runs of cable required, so the length of the cable reduces. So that reduces the ohmic loss. Secondly, as you switch to like cables with the more cross-section area. For example, you can go from 4 to 6 mm square. So then also you can reduce the ohmic loss. And maybe I think Omar I would then pass this question to Omar for this.
Omar, go right ahead.
Yes.
So we've actually ran all the Vertex series across all of our inverters, even the residential ones, right? So not only for utility scale, even for the smaller, like single phase inverters. And there's a trick you do there. If it's a multi-amputee inverter, you can operate it as 2 in 1, right? So you operate as a single amputee device, and you're able to actually take in the short circuit current. But basically, the full range is compatible with the Vertex series.
Excellent. Thank you very much, both Omar and Nasir. We have a question that has come through. There is a few, so I'm just going to go. One says, why all of 1,500 volt string inverters now have fans, and why fanless design concept is not followed in 1,500 volt string inverters? So I think this is for you, Omar. If you can take it, and then Nasir, feel free.
We've seen it, I mean, maybe a couple of years back, people tried to introduce fanless design into these inverters. And here's the case. One of the key determining factors of an inverter's lifetime is your thermal management, right? So if the inverter is, let's say the internal temperature of the inverter is fluctuating a lot, then that has direct implications on the lifetime of the semiconductors inside. And if you're going without a fan, then you have practically zero control over the internal temperature, and you will not have sort of reliable control there, right? Or reliable lifetimes. So that's why for most, let's say, bigger inverters, you will see fans now, even with manufacturers that have championed fanless design in the past. We've always been with fans for bigger inverters.
Thank you very much. There is a couple of questions more that have come through. You can see them in the list of questions. One says, do you think, and I opened them to both of you, do you think using a web design tool is enough to calculate the string layouts versus controller types? I think it's more for you, Omar, but you know.
I'm not sure what do you mean controller types? But I mean,
it's the first question. Then it says something Sunny Design Web.
Oh yeah, I mean, so Sunny Design Web is SMA's sort of sizing tool, and it's extremely popular. And I think it is enough to get an initial indication, right? So obviously it's not a full-fledged simulation software, but it's a great initial sort of, if you have many scenarios, you can probably create a space within where you will optimize. Right? So yes, it is more than enough, and you can actually now put string layouts inside Sunny Design.
And there is a lot of questions about string versus alternative inverters, which is not surprising and also surprising because we've been, asking these questions for so many years. But here Fayak says, compare between string versus central inverters for large-scale projects in efficiency and cost. So this goes to the two of you, Omar.
Yeah, do you want? I can answer that one real quick, right? So, age-old question of the century, string versus central. But I want to make also the distinction between multi-amputee string and single amputee string, right? So even when we go with string inverters, we go single amputee string because we want to retain the central architecture of the plant. So we don't want to see inverters out in the field. We want to see inverters clustered, right? So this is what we call decentral central. If you're operating in markets where, let's say, you don't have access to technicians, right? Your O&M concept is basically you want to switch out inverters. That's where I would say go for string, but keep it single amputee so you can sort of deconstruct the central inverter into multiple inverters, but keep them in the same place. Right? In places where, let's say, you have high inverter expertise, I would almost always, depending on the plant size, say central inverters will result in lower LCOE.
Nasir, I assume you don't want to add anything here?
Yeah, actually, from this point of view, whether to select central and string, from our side, we just ensure our compatibility with both the inverter types, and we just ensure from our side the modules would result in optimization for our customers when using, on either scenario. Yeah.
So you fight on both sides, so it's all fine. Makes sense.
Actually, no suggestion.
Makes sense. But it's a very common question, you know, like people ask it a lot. So this is why I think there is still an ongoing debate as to how do I suppose the real question is how do I calculate which is best for me? You know, that's, and that is like a much more nuanced. So there, you know, you can consider, you know, what effect does that higher module size on how do I calculate that LCOE? Okay, here we continue with the ones that they've just been sent, okay? We have, what do you prefer for system design with a high power modules with high voltage and low current, or the opposite, low voltage and high current? The first question, the one from Mohammed.
Right, so, I mean, you can make a case for both, but obviously with the Trina Vertex series, you're able to reduce the number of strings. And in this case, you can show significantly lower BOS. I think Nasir can also chat about that, right?
Yeah, from our side, I think that if you are going with modules with the you know, higher VOC, with higher VOC, then the disadvantage that those type of modules are going to bring for the system is that you will have shorter strings. So shorter strings mean more number of strings to reach the capacity of the plant. So I think there would be more disadvantages than advantages to that type of system, because you will be in total, you will be increasing your number of strings, increasing the number of modules and all the associated cost. So better to go with modules having lower VOC.
Thank you very much. And we have one more here in the list. Of course, you guys can always send more, but it says, what is the difference between a normal inverter and a hybrid inverter?
Oh, wow. Well, that's debatable. But you see the term hybrid inverter come up recently, which is basically an inverter where you can connect a battery and PV, right, on the DC side. So that's what we sort of call hybrid inverter. And actually for our utility scale, we're able to do that with our central inverters. So we're able to extend the DC side with DC-DC converters and couple batteries on the DC side.
Excellent, thank you very much. There is one question here sent by Ajay. It says, with AI drone-based thermal scanning, we can, oh no, this is just a comment actually. So let me bring out some of the questions that I had. Okay, so Omar, what is the potential yield loss when decreasing the amount of MPPTs in your plant? MPPTs being the maximum power point trackers. I actually made a point.
So we've actually done an extensive study on this, right? And most people tend to think higher MPPTs, higher yield. But we've actually even done simulated 18 megawatts in one MPPT, right? And going from one MPPT on 18 megawatts to, let's say, 64 MPPTs only extracts about 0.6% more yield, right? And that is sort of, if we have any economists out here, it's sort of law of diminishing returns, right? So going from 0 to 1 isn't the same as doubling every time. You'll get diminishing results. And some people tend to say, okay, but I want those 0.6%, but I say consider the costs of those 0.6%. Right? More MPPTs, more failures. Okay, more yield, but significantly more failures. Right?
So the calculation gets harder and harder in terms of the decision.
Yeah, but let's say don't overvalue your maximum PowerPoint trackers. They're good. One is good, 2 maybe, right? But 200 isn't. There's only marginal value you can extract with each additional one.
Excellent. Okay, so now how can you detect if a string is underperforming with only zone monitoring? Oh,
that is basically, you can detect it by detecting the overall zone, and that is really perfect for higher power strings. So if you have less strings, if you have 2 zones next to each other and one of the strings is underperforming, right, you will see that directly reflect on the zone, right? So, and if you have, like with Trina, maybe 15 strings per zone, then that is more or less 6%, and you can directly see that by comparing 2 zones across each other. So you don't need to have information at the string level. At the zone level, you can infer the string level performance.
Excellent. Thank you very much. I continue with some of the questions that I have here because we're running out of time a little bit. What is the price adder for higher current inverter models compared to same size, lower current inverters?
In our case, we give the same inverters for both, right? So there is no significant cost associated with switching to high short circuit currents. With the multi-MPT case, you will see people switching from 40 amp to 50 amp, right? On their DC disconnectors on each MPPT, but I would leave that to the other manufacturers to decide.
Okay, I have a few more questions here, but hang on, there is one here from the audience. What do you prefer to use inverter and solar systems with large scale with energy storage systems? What prefer to use inverter? I think the question is, what inverter do you prefer to use in large scale systems with energy storage systems?
Definitely SMA inverter, for sure. But I would say, I mean, I'm not sure what the question is really here. If you want to say DC versus AC coupled, maybe, right? Each has its applications, it really depends. If you're primarily looking at energy applications like energy shifting or arbitrage, mainly you go for DC coupled. If you're looking for more power applications like voltage control, frequency control, ancillary services, then you're going for AC coupled systems. I hope, oh yeah, that was the question. Yeah, I would say AC coupled. So it depends on the application. Energy applications, hybrid or DC coupled. Power applications, AC coupled.
So there's a question here from Mohammed for you, Nasir. It says, what do you think will be coming next for PV panel power and technology? It's a bit of a crystal ball question, but it's always cool. You know, what are you guys working on?
Yeah, I can say, I mean, still we have we plan to go on higher power, and then we are working on higher efficiency as well. So currently our products are in development stage, so won't be able to reveal much, but we can say that please stay tuned, and we might have, N-type modules soon. N-type modules with around 700 watt peak and higher efficiency, higher efficiency and better bifaciality and all those better degradation associated with N-type modules.
So it's about working on the numbers, so that they make more and more sense slowly, like little improvements, correct?
Yes, and as you know, we have come a long way. I mean 2009 up to now. At that time we had like 200 watt, and now we are at 670 watt modules. So yeah.
It's always incredible to me how far, the PV industry has been able to come, just based on small incremental innovation. Actually, I think it's outstanding, and it shows a really good case for why it's so important, to keep looking at the little things that make such huge difference in the long term. You had the same question for you, Omar, as well. What did you see in the inverter side, next?
It's really tough to draw the line where we can say stuff right now, but I would say at least recent activity that's been it's super exciting is grid forming, grid connected, right? That's where SMA is sort of pioneering the space there. So recently we've been commissioning, let's say, megawatt scale grid forming batteries and grid forming, but co-located with PV sometimes as well. Right, so grid forming is one of the major topics coming up, and then obviously hydrogen. And so both of these, I'd say, are two major topics.
Excellent. So do you want to add anything else, Nasir? We cannot hear you. Please switch on your microphone. We went the whole hour without one, but now it happens. Go, Nasir.
Yeah, I mean, so from my side, I mean, the parting words, I mean, thank you very much for arranging this webinar. We really had, insightful discussion. Thanks a lot, Omar, and thanks to all your audience. And please get in touch with us if you have any further questions related to my part. Thank you.
Yeah, excellent. Omar, anything you want to add? Just last words?
Same to me. Always a pleasure being here, and thank you for having us. And probably see you on the next webinar.
Yes, sounds like there is a few things that you guys are working on that are really interesting to follow, because at the end of the day, we're all here for one thing and one thing only, and it's the fact that we need to get better at the game that we're all playing, because there is quite a lot of competitiveness. We've done well. The PV industry has come a long way, but it's about the little nuances and the little calculations, and how can you understand the technology well enough that that you can deploy different part equipment in a way that you gain that little bit each time, and these are the guys that can help you with those things, with your calculations, with your way to finding your answers, because it's just about to get even more complex. As we're seeing it constantly, we're getting the announcement of the costs coming down, and that means that we have to just get better at the game. So thank you very much for attending with us. Thank you very much, Nasir and Omar, for sharing with us such nuanced and detailed information, and we will see you in the next webinar. Thank you very much. Bye.